Hello everyone, welcome to Ask Tutorial 3, Contract Storage and Simple Token. So in Tutorial 1 and Tutorial 2, we have covered how to write your smart contract and deploy them on a blockchain. We also know how to interact with your smart contract and how blockchain nodes actually execute them internally. So let's talk about contract storage. When we are writing smart contracts, we need this contract to store some data in the blockchain database. Just keep in mind, blockchain is a software that contains a database. You can think blockchain as a shared, distributed database with consensus. For example, in Ask Tutorial 1, we used @state flag bool to store the flag in a blockchain database. And in the metadata.json defines how it will be stored in the blockchain query database. Internally, Ask will convert the data types to scale codec so it can be serialized and stored as value in Substrate KV. The scale codec is the way how data will be serialized in Substrate. So all data to be stored in the Substrate KV needs to be serialized in scale codec first. So let's first learn what the Substrate KVDB looks like. The following schema depicts the storage that is exposed to Ask by contract palettes. This is the KV database of Substrate. You can see it is a KV, so each cell, the keys is always 256-bit, and the cell contains the value that are byte sequence. So remember last time we stored the we store the boolean. It just stores as one value in the cell in a key. So when we are trying to fetch the data, the contract first tells the palette contract the key, which the key is. The palette contract then fetch the data, and then we get the value. And when we are setting the value, we reset this value to the value to a different one, like we set from false to true, things like that. Or it happens just one cell of the value. Basic types. Ask provides its own data types that implementing scale codec corresponding to basic data types in assembly script and standard libraries collection. So you can think the data types here is Ask version, and the data types on the left is the data types that is native to assembly script. Each data type has its corresponding codec version that Ask uses. So basically you can stay with the data types in assembly script, and Ask will automatically convert them to scale codec. Aside from basic data types, we also need composite types. Composite types are like arrays, maps. Basic types will be stored as the value in the blockchain key database, key value DB. However, for large data sets, fetching the entire data sets from one cell of value is not efficient. In Ask, to store large data sets such as map and array, Ask provides two storage methods, spread and packed. More specifically, Ask provides spread. For spread storage modes, each storage unit has its own storage address and it will only be loaded when needed. So thinking about a map that has 10 keys with 10 key value, it will occupy 10 key values in the DB. You can think each cell only stores one key value pair. And for the spread storage modes, we provide spread storable map and spread storable array. For the pack storage modes, all storage units need to be serialized into a set of data streams and stored in one shared address. When getting the data from pack storage, the data will be fetched only once. Therefore, pack storage isn't desirable for accessing data in large volume. Let's look at this schema here. Suppose you have an array that is 20 elements. You put all 20 elements, you serialize all 20 elements into bytes and store them as one value in the key value database. Let's look at spread storable map here, since we are going to use this data structure in the demo or in the codes we are be doing today. Spread storable map is a map stored in spread modes, meaning each key value takes its own address in Substrate KV database. Here are some common functions that you might be using today. It is set, get and delete. Set basically sets the key v. Get just get the key per get the value per key, and delete just delete this key value pair. And pack storable map, if you have understood the stuff we talked before, pack storage map is a map that is serialized and stored as one value in the substrate key value DB. So it will only occupy one cell of the key value DB. So today's task will be implementing a simple token. The simple token does only one thing, that is the font transfer. Suppose you have one token, suppose you issue a token that only allows people to trade them, and it doesn't have to be connected with other applications or dApps. So the only function will be font transfer. And the reason we're doing this because in the next tutorial we'll be going more deep with ERC20 standard tokens. And so we will need a transfer function that transfer balances to target address and a transfer event to be emitted while we're doing the transfer. Let's start the coding. All right, so let's start doing the code. So the target for today is just writing a simple token that allows users to transfer tokens among them. So first we need a transfer function and a transfer event that is corresponding with it. Before we actually writing any event or contract codes, we need to import the dependencies we'll be using for today. So we first need the account ID. Account ID is the system parameter. For more details, you can always look at our Ask documents. This is the parameter that communicates with pilot contract. because each packet contract receives certain data structures. And we need a spread storable map. The purpose of this map is just to save the balances of each account. Like you have like Bob sends balance to Alice. You need a spread storable map that stores each one's balance. MSG is the environmental variables that you will need to get the sender's address, the block height. We have covered this in tutorial 1. Event is the basic class you need for emitter for declaring a class. U128 is the data of your balance, and uint 128 is the scale codec version. You import them from AskLang. Okay. So once you have imported dependencies, let's declare the event we'll be using for today. So you need a transfer event that extends from the basic event. And you need the topic from account ID, another topic to account ID, because a transfer always contains a from and a to, which is the sender and recipient. And amount means how much amount you are sending. Then for this class, you need a constructor, which is from account ID to account ID and amount. First, you call the super. Then you set this dot from equals from, this dot to equals to, this dot amount equals amount. Simple. All right. So once you have this event, that's we need a contract that stores the balances and able to transfer funds between different parties. Now let's write up the skeleton for simple token. Okay, first you need to declare a contract. Let's use this decorator to declare a contract. Let's call it simple token. And then let's declare the storage we'll be using. We call it balances to track the balances of each ID. We put state because this is the storage that will be synced to the blockchain database. And we'll be using storage storable map as the data structure. We use account ID U128 as the balance of this account ID. We initialize this with new spread, storable map, account ID. Then you need a constructor. It will be leave empty. because for contract constructor, we have our own implementation. Okay. Let's talk why we are now using a packed storable map. The reason we are using spread storable map over packed storable map is that we can estimate the size of our map as we have no idea how many accounts will be stored. Suppose you have like 1,000,000 accounts using this token. Fetching 1,000,000 records at once isn't a very good idea. So we use spread storable map as the balance storage type. Let's write up the constructor. The constructor is where you instantiate your contract. You need a constructor. You construct a decorator. You put default. Initial balance. The reason we are doing this because if you issue a token, you need some like total supply. The total supply will be given when you instantiate the contract, right? So we usually just give the initial balance to the initial caller. So if I'm the initiator of this contract, I have all the balance in my account for now. So let contract caller equals msg.sender. This is just get the caller of this contract. Or the one who instantiates this contract. This set. Remember, set is just insert a key v into this map. Contract caller new u. The reason we are casting this initial balance to u into 128 is just because this is a map that has to follow scale codec. So it only receives value that follows scale codec. So this is something we can improve in the future, that we're making sure you can only use U128 all over the place, not doing any casting. But we are working on it right now. New transfer. Remember, anytime you just doing any changes to the blockchain state, you have to emit an event so the outside world knows what happens. Since the thing because there's no sender, you have to use no as the sender, because this money comes from nowhere. Remember, we issue it at the beginning of the blockchain of the contract. Initial balance. All right. So this is our constructor. The second one, let's write some public functions. The first function we'll be using is a function to check the balance of your mutates false, because this one just checks the balance. It doesn't mutate any blockchain state. So this one doesn't require to you need to put mutate equals false, as it does not change any blockchain state. And logic is very easy. You just get the balance of the color. Sorry. You need to say balance of, and the parameters is account. Type will be account ID. U128, and just get the balance first. This dot balances dot get. The balances is just a map file, so just call with the account, and you need to check if this balance exists, right? So if you are, because there's no guarantee that this account will exist in your balance map, you need to making sure check if the balance is valid first. Otherwise, you may return some like null or something, right? Like suppose you don't, this account ID does not has any token, you should return 0. To call this, because the value you're getting is a codec value, scale codec. You need to unwrap this. Otherwise, you just return U128.0. All right. So next, we need a transfer function that just transfer the font. And this one, message. This one, it is just simple as transfer the font from one entity to another entity. So you need a recipient, account ID, font. So the sender is the message caller, and the recipient is the one you want to send the font to. And it should return Boolean. If the transfer succeeds, you should return true. Let from equals message.sender. This is the caller of this contract. This dot that's not writing this transfer function for now, because it's good. It's a very good habit to separate functions from internal functions that can be used in other functions. It's just a convention of writing code. Return true. All right. So now we have the skeleton of the public functions. Let's write up the functions that are internal functions. So first we need to protect it since it's internal, and we may use this in future because Ask is the language that supports inheritance. So let's not use private for now. So it takes a sender, account ID, recipient, type account ID, and amount. And let's work this out. Remember, it returns void as the return structure. Okay. So what do we need in transfer? First, we need to check if the sender account ID and recipient account ID is not null. If it's, you can't really send from a null account to another null account, because otherwise you will lose fund in middle of the transfer, or you credit someone with, you can send from null account to someone, then you basically credit yourself with free money. That's not allowed. So first we need to do this, let's first assert that sender dot not equal account ID dot null. Transfer from your 0 address. Then need to assert the recipient is not null. And giving the warning message that transfer to 0 address. So first, those two are not allowed. We shouldn't allow them to happen. Then we need to get the balance of the sender and then subtract the amount that we want to transfer. Okay, let's let spender balance equals this dot balance of. Since we already have this function, right? So let's just call this sender. And we assert. We need to make sure this guy has enough fund to send, right? So the balance, the remaining balance of the sender has to be larger than the amount where he is sending out. Spender balance larger or equal to amount. Otherwise, we'll give you a warning message: transfer amount exceeds balance. Okay, now let's calculate the balance left. So let sender left equals spender balance minus the amount he's sending out. Then this dot balances dot set sender new. You set the remaining balance back to this guy, right? So once he's sending out the amount, we are setting the remaining balance sender left, and then you need to set the balance of the recipient. So that's recipient first. You need to get the balance of the recipient. Then you just need to add the amount that is from the sender. Then you need to set the new balance of recipient back to the map. Balances dot set recipient, new recipient left. Once you have finished all this, remember every time you change the blockchain state, you have to emit an event. So let's emit an event. Transfer. Remember, it takes 3 parameters: sender, recipient, and amount. And you need to emit this. Great. Let's try to compile it. You just go to simple token and then you do npx pl ask cli compile. Cl contracts c.ts. You just compile it. Since I already compiled it to save some time, let's look at the compiled one. So this is the final compilation. It's the metadata, and this is a WASM. The metadata contains all the ABIs, and this is the actual code to be deployed. Okay, let's deploy them in using our Europe UI. It's same as last time, just making sure you upload and deploy them. Just upload this one here. First upload the metadata, then the WASM. This one here. All right, I have deployed them, so let's go to the instance. So you can see it has balance of function and execute. That's the transfer. So let's roll back some of the roll back to test them. Roll back to initial state. So as you can see, this one is instantiated at block 3. So let's go back to block 3. As you can see, now we eliminate all the calls we have done. That's a great feature of Europa. It allows you to go back and forward to just focus. You can focus on your own testing. Let's go to contracts instance. This one here. So you have balance of. That's because we use Alice to instantiate this contract. He's the sender, so he should get a balance of what we set here. So you can see, since we set the balance to be 1 billion in the beginning, now he has a balance of 1 billion. So now let's transfer some of the balance out. Let's transfer to Bob. And the amount, let's do it's 1,000. Then the caller is Alice. Let's do execute. Maybe bug out because I'm running this on a virtual machine. Sometimes it just got stuck. Start. Let's do the transfer again. Simple token. Just check the balance again. Red. Then do the transfer to Bob. Okay. Execute successfully. Let's see. So this is how it gets executed. That's just how it gets executed in details in the blockchain. You can see it has a lot of sell and get, and mainly the gas cost is consumed with those host functions. So if you can write your contract using fewer host functions, you are a very good contract writer. Meaning you saving a lot of gas, right? So let's check the balance of Alice. So she should be deducted with 1,000 as his initial balance. What's going on? CPU Bob. Execute correctly. And the balance of Alice should wait a second. Oh, because I set amount to let's do this again. Functions execute transfer. Oh, because we send 0 balance amount. Sorry. Let's send this to 10,000, 1,000, and execute. And then we should get the balance of Alice. Okay, you can see the balance has been deducted correctly with 1,000. Then let's check the balance of Bob. 1,000, yeah. So this is just a demonstration of how to write a simple token that only has one function, that is transfer, and one immutable function that just checks the balance. So ERC20 is based upon this simple token with some additional features such as setting allowance to allow someone else to use your balance. So it can be interacted and combined with other smart contracts. So we will be covering how to write your ERC20 contract in the next tutorial. Thank you for watching. Please stay tuned for the next tutorial.